Welcome to Finite Element Methods. Today we'll be discussing the 1D finite element formulation for the order Bernoulli beam, and I'll be discussing how to formulate the formulation for the 1D order Bernoulli beam. The ideas in finite element analysis are to really approximate the solution to a partial differential equation that governs the behavior of a structure over a very complicated domain. And the idea there is to break up the problem into pieces where we can actually uh, try to break up into pieces where we can actually now solve the equations a little bit easier in a more simple domain. And then bring everything together and assemble it. And the way we learn how to do that is to formulate the element behavior, deriving the weak form of the partial differential equation. We use an approximate solution over a domain, and it will be an element. We're calling a subdomain an element, and then we'll determine the element stiffness matrix and force vector that correspond to that element. We then discretize the domain of the structure into elements. We assemble the stiffness matrix and force vectors together, impose the essential boundary conditions and the natural boundary conditions, and then we're able to then solve the algebraic system of equations, post-process the results, and determine the variables of interest. That is the idea of finite elements, and that is an exciting thing that we can take a governing equation over a complicated domain and turn it into a simple algebraic system of equations. Not always simple, but in most cases we can. And so today we'll be discussing a very special topic, and in this case, we'll be talking about representing beams. Now, what you see here is a tower, like an electrical tower, that's supported by beams. You can see here there's cross members and support beams that are forming this particular structural civil engineering structure. And the point I want to make here is that we could model these things as 3D elements. Of course, this has a finite cross section, and I could potentially represent this as 3D elements, but that'll be computationally expensive, and it's not really required for this problem. We could potentially, instead of representing this as 3D structures, represent that as a beam and just model that as a wire and just pretend that the whole cross section follows the deformation of that wire. That'll be computationally a lot more inexpensive. On the right hand side, you see a bridge that's supported by cables and beams. And very similarly, we could represent that beam as a slender wire structure, and we will then determine the behavior of that structure by following that wire, and that deformation of the wire is basically the deformation of that whole beam. Now, you may say, well, the applications shown here are civil engineering applications, but I'm not seeing an application for aircraft. Well, that is not the case. In aircraft applications, you have stiffening members and longerons that run across the whole aircraft. These representations could be developed using 3D models. But these 3D models, again, are computationally expensive. We want to find approaches to solve these problems in an inexpensive manner. And to accomplish that, those stiffening representations can be performed using beam elements. So that is the idea that we have here, is how can we simplify the problem, and how can we go about that? Order Bernoulli beam in the 1750s had a primary assumption that he put forth, and is that under deformation, for very long beams, they're slender, and that means that the length is typically longer than the thickness by 15 times, that the cross section stays perpendicular to the neutral axis. That in fact, this cross section here, and I'm talking the cross section of this beam, stays perpendicular to the neutral axis during deformation. And that really simplifies a lot when it comes to the formulation for order Bernoulli beam. This was covered in a mechanics of materials course, but perhaps they didn't go into the level of details required to understand this theory further. The beam is subjected to a distributed transverse load. It has a transverse deflection that I'm calling W of X. And if I look at any cut here, like a free body diagram, you will have a shear load and a bending moment that's reacting the external loads. And recall the shear and bending moments are really quantities that are somewhat made up, but are very useful when it comes to describing a beam. Because in reality, when you apply transverse load to a structure, it gets reacted by stresses, right? But here we're saying they're getting reacted by shear and bending moment. And that is an interesting idea. Um, we won't have the time to go into the theory for why that is, but it does simplify things a bit when it comes to beams. And I already derived these equations, but it's worth kind of reminding you where they came from. And the idea was that if I take a little piece and apply a load Q over here, and I'm basically taking a little cut from here, this beam, and drawing it here, and that's your section dx. On this end, I have a bending moment. On this side, I have a bending moment plus dm. And what you have here is a shear load and a v plus dv on this side. So we can apply equilibrium. You can using mechanics of materials principles or statics of materials, static strength of materials. And here I'm using equilibrium by adding forces in the in the vertical direction, and my coordinates are such that y is the vertical direction, while x is the axial direction, and z is out of plane on this page. With that said, I have V plus Q dx. Q times this dx gives me the load that's acting on this little piece in the y direction, minus V plus dV, which is the force, shear force on this side of this little piece. And what I have here is that this is equal to 0. Now I can solve, and I will have dV dx equals Q. We can then calculate the moment equilibrium. In the moment equilibrium equations, we have this moment, and if I take the moments, we could take the moments about the center. You can choose where you want to take them. Here I've chosen to take the moments about this side so that V plus dV do not show up. So I have M plus V dx, V times this length dx, the lever arm, plus Q dx, which is a force due to this distributed force, times dx divided by 2, because that's the length from the centroid of this distributed force to this face, minus m plus dm, which is the moment on this side at a distance dx. And as dx goes to 0, you can find that dm dx equals v. And then the second derivative of the moment with respect to x is q. You can see here that came from substituting this expression into this expression here, and that gave me that expression there. And we further discuss how the cross section is stays perpendicular to the cross section, and that the slope dw dx provides me quite a bit of information about how that neutral axis deforms. We also have discussed that the typical assumption here is that the deflection, the axial deflection is such that you can see this point here. This point here moved to the left when this deformed. You can see that this point also deforms, but it moves to the right with respect to the neutral axis. So in essence, what you see here, blowing it up, if you blow this up, you can see that this point moves to the left, this point moves to the right, relative to the neutral axis. And we can assume there's a linear approximation through the thickness. And if we do that, then the axial deflection is minus y dw dx. And this comes plainly from geometry. The axial strain, and what is it saying is that at y equals minus h, at y equals h half, which is the top surface, this point will move to the left by this much, and this point here move to the right by this much. And we've already discussed this quite a bit in a previous lecture, but we are kind of reminding you about what we're doing here. The axial strain is really the derivative of u respect to x. And as a consequence, since I have this expression, I can take the derivative very easily, and I get minus y, and I have this curvature term. This term represents the curvature of the beam. Now notice how this strain depends on y explicitly, but depends on w, which is a function of x. We also talked about, if I look at the cross section of the structure, y going up, x going outwards, to the face, the surface. Here you have the stress quantity sigma xx, which acts in a small little piece. And dm, the differential moment due to this area, which has sigma xx applied to it, will be sigma xx times y, the distance, the lever arm, and is negative to maintain a positive. So it's positive about the uh, x direction. I have minus y sigma xx dA. And so now I can integrate this equation over the area, and I get m equals minus y sigma xx dA. And if you recall, sigma xx equals E times epsilon xx, I can plug that in. I can plug in the idea that the stress equals the modulus times the axial strain into this equation. And I'm going a little bit faster because we already derived these equations. And I really invite you to pause and kind of re-derive them and make sure you understand the concepts. So here what I have is epsilon xx was previously calculated as this expression. And I plug that in here and I get y squared now. The minus and minus cancel out. And get this y squared dA. None of this term E or the second derivative of W depend on the cross-sectional area because they only depend on x. I can bring that outside of the integral. And perhaps I get this expression here, which you can see. And this is the moment of inertia, the second moment of inertia. So I get EI W double prime. So the moment becomes EI W double prime. I know where E is the modulus, I is the inertia of the cross section. All I have to do now is plug that in here into this equation to get the differential equations for a beam. And this equation we derived earlier in time, but we kind of re-derived it again for reminder purposes. And recalling this information is very useful because you get connected to what's going on. Here, Q is the distributed force, transverse to the beam. W is the transverse deflection. I is the second moment of inertia, and E is the modulus. This information together provides a lot of great
You guys only use UCLA
approaches.
planning for your email.
And so I want to solve this Goran equation next. And so how do I accomplish that? So I have the boundary conditions for this problem. We already learned where they came from, and we're going to look at that again today. But W specified or W prime specified, those are the essential boundary conditions for a beam. W is a transverse deflection, W prime is a slope. If you specify both of these in a particular location, that's a clamped condition. And if you specify W, that's more of a roller type condition or simply supported. Here, EIW triple prime at 0 is the load applied that's transverse. And EIW double prime at 0 here goes along with the W prime. And that's the bending moment specified. I can also specify certain boundary conditions at x equals L. I want to point out that this is the strong form of the problem. And that is a mathematical statement about the solution at every point in the domain. Here, this should be W of x. I apologize. And so what I'm going to do now is derive the weak from Galerkin. And we learned that deriving the weak from Galerkin has several advantages. We could have just stuck with the strong from Galerkin as extensively discussed in my book. We have several examples that show that. But there is a benefit to going to weak from Galerkin because in the weak from Galerkin, you can decrease the continuity requirements for the approximation function, number one. And number two, we only have to satisfy the essential boundary conditions with approximate solution and then use the weak form to satisfy the natural boundary conditions in an implicit manner. So here, I'm going to take the residual and make it orthogonal to these weight functions, V, and set that equal to 0. By doing that, I'm making the residual function orthogonal to V. And my goal is to select an approximation for W. And for each of the trial functions or basis functions that make up W, those are the ones I'm going to make this residual orthogonal to V. So there's a benefit here. So now this is a very high order differentiation to fourth order. So we're going to reduce the order integration. And we've already done this a few times, but I'm going to do it again. And I'm going to take now this, put it on the right, and the V on the left. And I'm going to integrate by parts one by one. So I did it once and once again. And I have now the same order differentiation on both sides. Now I can drive plus, minus, plus, and notice how this become boundary terms and this goes back into the integral. And notice how I had a fourth order differential equation. Now it's a second order differential equation. I apologize, that's an incorrect statement. I have an integral that contains quantities, and the highest order derivatives on each of the variables is second order. And that's what we're talking about here. Q times V, nothing happens there. We don't have to touch that. This cross term becomes this term here. This cross term becomes this term here. And notice how we had discussed earlier how EIW double prime was moment, and EIW double prime, which is moment, the derivative moment is shear. So it's very interesting how I started with the governing equations. And by deriving in weak form, I actually end up with physical quantities that we know a lot about. So that's a very powerful idea that we have in our hands, and it's showing us that weak form Galerkin can actually connect us to the physics of the problem. Um, Now note that the weak form of the problem can be written in this manner, and that the highest order differentiation now is second order. And now we can identify the boundary conditions. I can look at here that V can be looked at as analogous to W, and V prime is analogous to W prime. So anytime I have anything specified on W or anything specified on W prime as part of the governing equation provided to you, that's going to be the essential boundary conditions. Notice how automatically this underlying statement here is the moment, and the underlying statement here is the shear. And you may have forgotten why, but we just derived it. So let me show you that again. See, look at how moment is EIW double prime, and look how the derivative of the moment is shear. So clearly, we are in the right track. We haven't made a mistake. Everything is correct. And here, that's the moment, and that's a shear. And that's beautiful. We connected the reality of the problem to mathematics, because I could have given you this governing equation in vacuum and asked you to solve it. But it's really cool how, when you derive the weak form, you actually get quantities that have physical meaning. And that's quite exciting. So we already discussed this, but it's worth discussing that. I can expand this term. So this shear here can be valued as 0 and L. This moment can be valued as 0 and L. When you expand that, you get this expression here. And I'm going to further make things more systematic. So you can see this moment is going clockwise. I'm going to make it counterclockwise and call it Q2. This shear here is going downwards. I'm going to put it going upwards, and I'm doing that to keep the sign convention simple. And you will see that now this moment goes to counterclockwise. This moment also goes counterclockwise. And these shear loads go both in the same direction. That's very convenient. But to do that, you have to put a minus sign, and that's what you see there. And here again, a minus sign on the moment, and that's what you see there. Once I do that conversion, you can see here now that everything has a negative sign, so everything's consistent. The shear force is acting in the same direction. The bending moment is also acting in the same direction. That's actually convenient to do. You can also see the definitions for Q3, Q1, Q4, and Q2 are given here on the right-hand side. And that's going to help create an approach that's systematic so that everything is consistent. And again, that's very exciting. When you're working on problems and you're able to do things like that, it does make things systematic. And that's the exciting part about finite elements. If we can find those tricks, those little tricks are going to help you make the problem more systematic. That's the direction we want to go. One thing I want to point out, this is a second order differential equation. Another thing I want to point out is that I have 4 degrees of freedom. I have, and I'll take you back to that in case you've forgotten. So I have the deflection at this point, but also the slope. And then here I have the slope also and the deflection. So I have 4 unknowns. And these 4 unknowns, the best representation for 4 unknown coefficients is a polynomial of cubic degree. And why is that? With four unknowns, I have C1, I have four unknowns here too. That's why cubic polynomial is the best. Because I have a deflection on either side of the beam, and then I have the slope at either side of the beam. And those are the quantities that have to be part of your approximation function. The reason for that is because we demonstrated that the essential boundary condition for me to have continuity requirements across elements, the deflection has to be continuous, and the first derivative of the deflection has to be continuous across element boundaries for this theory to work out. And how do I know that? Because I can look at the essential boundary conditions and they guide me into what is going on. That is what's helping me understand what is going on. So I have four unknown nodal quantities, two node per node, and I have a cubic polynomial. I also know that the deflection on the left side of the beam at zero, x equals zero, is V1. And on the right side of the beam at x equals L is V2. W prime at zero is theta 1. W prime at L is theta 2. And we have four unknowns here, C0, C1, C2, C3. But I already told you a few times through a few derivations that that is actually quite inconvenient. It's better if we can write the unknown coefficient in terms of unknown nodal quantities. And I've done that by, I want to relate the C naught, C1, C2, C3 to this V1 theta 1, V2 theta 2, because these unknown nodal quantities do have physical meaning. So at W naught, I can now plug in W naught. I have this equation. At W prime 0, I have this equation. At WL, I have this equation. And at W prime at L, I have this equation. I have four unknowns, which I can now write in terms of V1 theta 1, V2, and theta 2. So let's solve for C1, C2, C3, C4 in terms of the nodal deflections and slopes. So this is an error. We have to solve for C naught, C1, 2, C3, and C0, C1, C2, and C3, not for C4, I apologize. And so now we're gonna go ahead and do that. I can put this in a, remember, when you see equations, you can put it in matrix format. You shouldn't be too worried about the way it looks. It looks scary, but it's not anything scary. If I multiply this row by this column, I get that first equation. Multiply that second row by that column, you can see I get that equation too. So no need to worry about how it looks. I will not be worried at all. And so here's what I get. I want to solve for C naught, C1, C2, and C3. And when I do that, I get, I can invert this mathematic. I don't need to do it by hand. And when I invert that, I can find the basis functions as I discussed in the previous lecture, previous few lectures ago. I take the partial W prime tilde with respect to V1, and then I can get the shape functions. And the idea here is I get W tilde as a function of X is V1 N1 plus theta 1 N2 plus V2 N3 plus theta 2 N4. And this is what I can get N1, N2, N3, N4 by following this procedure in Mathematica. It's a very powerful idea. It simplifies the way of how to do it by hand. But the idea is if I plug in W tilde at 0, I need to get V1. These shape functions are found in such a manner that W tilde at 0 should give me V1 because that's exactly what should happen at this end. At this end, W at 0 should be V1. W at L should give, all this should be 0 except for V2, and you should get W at L is V2. W prime at 0 should give me just theta 1, and W prime at L should give me theta 2. And so this has to hold because those are the unknown quantities at each of these nodes. When you do that work, when you go through this process to find this N1, N2, N3, N4, you will find that the shape functions or the trial or the basis functions look like this. And they look strange, but these are the shape functions. What I want to point out is that these shape functions or the trial functions are exactly 1 at the node that matters, but is 0 at the other nodes. You can see here that x equals L, this goes to 0. Sorry, at x equals L, I do get a value of 0. at x equals 0, I should get 1, which is exactly what you get. And that is exciting if that we were able to do that. I invite you to check the rest. Bottom line, these shape functions go into this row, and the column vector is the column vector of unknown coefficients that are nodal values that are unknown in this case. So I'm going to call this M bold. I'm going to call this D bold. And these shape functions do have a name in industry. They're called the cubic interpolation functions or Hermitian interpolation functions. So you may see that in the future. I can plot them so you can see what is going on. It's kind of useful to see what's going on. Let's plot N1 here. You can see how it drops. You can see how this curve N3 increases like that. So that's why they're called shape functions, because they do have a physical meaning. And notice how this shape function N1 and N3 is one in the respective node, but there are 0 elsewhere. And so now I'm ready. I'm ready to do some damage. How do I do that? I have this deflection, which I know how to approximate it now using these shape functions. N bold times D bold. Now the idea is to just plug that into the weak form. And we already learned how to do that. Remember, for W, we're going to select the approximation function. For V, we're going to select each of the shape functions. And the idea is, now when I look at this, though, notice how we have to calculate these W primes. So let's just do that. Let's calculate W double prime. You can see that there. Let's call this B bold. And that's the whole idea of finite elements, is to keep things very simple so you can actually apply the ideas quickly. And I can find the double derivatives of N1, N2, N3, and N4. You can see them here. I know the shape functions. I have them. It's a matter of just plugging in that into this expression. So now I have this W double prime. What else do I need? Pretty much now I have to just plug in V and W. So let's go carefully equation by equation. So for the first equation, I have a W double prime here, and W double prime is B bold times D bold. I already showed you how we find that. So that's what I did. For W double prime, we have B bold, D bold. Then I have this V double prime, and for V, I have to plug in N1. So I have N1 double prime there. For this one, I have N1 there, so Q times N1. And then I have to plug in N1 here in each of these coefficients. Now, when I do that, you will see that for the first equation, the only one that should survive is this one, because the shape function is 1 at that node, is 0 at the other nodes, and its derivative also will go to 0. So this will be the only thing that remains. The second equation, very similarly, let me repeat again in case it was unclear. For W double prime, I have to plug in B bold, D bold, because that's what that is. So I've done that. And I have here a V. For that V, I'm going to put N2, right? And for that, I get N2 double prime. Then for V, again, N2. You can see that there. And then I plug in N2 in each of these coefficients, and you will see that the only thing that will survive is that this will be a 1. It has to be that way because of the way that these shape functions were derived. And then I can do the same thing for the third equation and fourth equation. And if you notice very carefully, this column, if I put all these things into equations, you will see that I have this column vector. N1 double prime, N2 double prime, N3 double prime, N4 double prime. Isn't that the same thing as this B bold, but transpose? So yeah, the whole idea of finite elements is to write things very quickly and quickly. So I'll put that column vector as B bold transpose. And then this N1, N2, N3, and 4 is also a column vector, which is a column vector of N bold, if you recall. That's where you approximate a solution. W tilde is the shape functions times this column vector, and that row is M bold. So I have M bold transpose. And notice how when you work through all this, you're going to get Q1 for the first equation, Q2 for the second equation, Q3 for the third equation, Q4 for the fourth equation. So in reality, you get Q bold, and Q bold is made up of Q1, Q2, Q3, Q4. Now notice that this term has no D bold, so this can be brought to the other side of the equation. And so now you have D bold, which contains the unknown coefficients. They're the nodal quantities that are unknown. All this stuff here is numbers. The force you apply is a number. The concentrated force you apply is a number. So the only thing that's unknown is D bold. And that's exciting. We're able to turn a governing equation into an algebraic system of equations. Now recall that we can go from the strong form to the weak form, which is what I just did. I can also go from the total potential energy down and get the same answer. So let's see, what if we did that? So recall that we already showed that the total potential energy of a beam, when minimized, gives the weak form of the problem. We already showed that before. And so I'm not going to repeat that. But I want to show you that if I use the total potential energy, which was derived in a previous lecture, and I were to rewrite the total potential energy, so it looks the same. I mean, this thing is the same as that. There's no question about that. This transpose of a scalar quantity is the same thing as W double prime. So it's a constant. It doesn't matter. It's a little trick. Now notice that W double prime was B bold, D bold. We talked about that here. W tilde double prime is B bold, D bold. So I can plug that in here. I can plug that in here. I can plug it in here. I can plug it in here. Here it should be N bold, Q bold, D bold. And when I do that, I get this B bold, D bold here, B bold, D bold here, right? For W, I get M bold, D bold, as you see here. And now notice how the D bold transpose can be written in this manner, and D bold can be factored out in this manner. And that this D bold transpose can be factored out, and all these will have a D bold transpose factored out. And I'll let you do it with calm, and you will see that this is exactly what you will get. This is very powerful because I already showed you that the TPE for this problem is this, and this should not be equal to 0. I apologize, that's a mistake. And to minimize, now I have written the total potential energy, so it's only a function of this D bold. It turns out that D bold contains V1, theta 1, V2, and theta 2. So to minimize this pi, this total potential energy, I have to take the derivative of pi with respect to V1, theta 1, V2, theta 2. And I won't do it here, but when you do it step by step, you will see that I get the same set of equations as a weak form Galerkin. And that is a mathematical miracle that's worth pointing out again. Once again, I went from the governing equation to the equations of equilibrium for an element. And then I started with the total potential energy. And then I ended up in the same place. So that is exciting because two ways to approach a problem, I got to the same place. I won't do it here because you can use Mathematica very easily. So if once you have B bold, which is this, in Mathematica, you can go ahead and plug it in. Plug it in, do this calculation here, and you're going to get the stiffness matrix. That's what you get. M bold is this one, which was shown earlier. And all you have to do now, this is your element stiffness matrix and the force vector that corresponds to this beam element. Very exciting. If you were to have a distributed force, like this Q was constant across the element, that's easy. That just simply is going to turn out to be this when you integrate it in Mathematica. If you integrate this in Mathematica, this is what you get. Very simple looking equation. It is worth noting that QL divided times 6 divided by 12 is QL divided by 2. And QL divided by 12 times 6 is also QL divided by 2. That's interesting because the distributed load is Q and the length is L. So the total vertical force is Q times L. And what this Feynman code is saying is I should put half here and half here. I'll let you figure out why the moments, why these quantities corresponding to moments are the way they are. I would like you to think about that. And as you think about that, let me know what you find because you'll be very, very surprised about what you find. And it's actually an exciting finding as you work through that. But I won't spoil the surprise for you. I think it's better if you tried it yourself. So let's consider the following problem. I have this beam and I have this simply supported location here and here, rotor supports, and clamped here. That is very inconvenient. If I select a single beam, if I try to approximate a solution over this domain, it's going to be a pain to do that. I also have a couple applied here and a transverse load applied here. So I need to find a way of solving this problem. Well, let's discretize the domain into three elements. Element number 1, 2, and 3. And I have bending moment in theta 1 here, bending moment in theta 2 here, and so forth. I have P1 and V1 here, P2 and V2 there, and so forth. So 3 elements, 4 nodes. At each node, I have 2 degrees of freedom that are unknown, the deflection and the slope. And corresponding to the deflection, I have the shear force. Corresponding to the slope, I have the bending moment. So that's what I have. That's the way I've discretized it. So for element number 1, it's very easy. For element number 1, we're occupying the 4x4 here. So this is one way to do element assembly, by the way. You can expand the whole matrix so it looks this way. Let's look. So how many nodes do I have? I have 1, 2, 3, 4. And there's 2 degrees of freedom per node. I'm doing a little bit differently. In my book, I do it a little bit differently. And I provide the codes that you can write in MATLAB there so you can then write you can solve the problems quicker. But I should have an 8x8 for a 3 element. And so the first element occupies this space, obviously. And the second element occupies this space in the 8x8. That makes sense. Because it relates to nodes 2 and 3, and that's element 2 connects nodes 2 and 3. So it makes sense that I have this connected to this middle set and then this set. For element 3, that goes to the very bottom right. You can see here that belongs to nodes 3 and 4, so that makes sense. Nodes 3 and 4 for element number 3. You can do the old school way that I showed you was using the element code numbers. You can also do it that way. Both will provide the same answers. But I already taught you how to do the element code number approach. So I thought it would be cool to show you a different way of doing it. Now what you can do, you can assemble by adding all the stiffness matrices together. You just add them up like this, and it adds up in this manner. You can see that. The left-hand side becomes your forces. The right-hand side are the deflections are unknown. Now you can apply the boundary conditions. Let's look at it quick. Here I have a clamp condition. It's pinned here and pinned here. So I go here and apply the boundary conditions. It's clamped. So the first node is fully clamped, so that's 0. Then in the second node, I have it pinned, so there's no transverse deflection. And the third node, I also have it pinned, so that's 0. On the left-hand side, I should input the natural boundary conditions. In this case, you can see that the clamped end is fixed, so I don't know what the reaction forces are. I also know that the deflection is fixed, so I don't know what the shear force is, but I know that there is no bending moment applied at that node 2. You can see that in this problem. There's no couple applied here at node 2. So that's 0. Node 3, the deflection is specified as 0, so P3 is what is not known. And the bending moment at node 3 is a couple that was applied. You can see that there. A couple was applied. And so I don't have to return to this page. Notice how I have a downward force applied. Now I have a negative sign here because the bending moment convention I have is going counterclockwise while this couple goes clockwise. And so I have to be consistent here. And that's where you see a negative sign there. Then I have the shear force applied. And there's no bending moment applied at that node 4 at the very end. You're ready now to solve the equations. You can cross everything that's 0. And then you're left with 4 equations for unknowns, which you can quickly solve. Once you know the 4 unknowns, which are theta 2, theta 3, v4, and theta 4, you can plug that back in and then multiply this matrix times this column vector, and that'll automatically give you P1, N1, P2, and P3, which you can see here. I've also simplified the matrices for you so you can try it yourself, and you will see how this works. Very exciting stuff. Very exciting stuff.
I have a question, Professor.
So I do like your question. Just want to cover it really quick. So this is the element stiffness matrix. This, of course, was for a uniform shear distributed force, but that is the element stiffness matrix, and this applies to every element in the way I divided it. So there's nothing here that needs to be done in addition. The reason you see a difference here is because I put the 2 here, but 2 times 6 is 12, which you can see there. So everything is the same. You can use that element stiffness matrix to solve the problem. Nothing else there. You can also look at clamp beam, and I can bore you with examples, but I think the ideas are the same. I'll just, since the distributed force ended here, I also have a force applied here. I'll go, and these lengths are different, A and B. I think this is a good example. So divide this domain into 2 elements. Again, same idea. V1 and theta 1 are unknown in these nodes. Well, we know them is clamped. V2 and theta 2 here at this node, and then V3 and theta 3 at this node. Transverse, deflection, and slope. I'll use the same idea. Element number 1, use the equation that we already derived for the element formulation, which was given here. That's the element formulation, but the length now is A, right? So the length is A in this scenario. So the length is A, so plug that in there. I have 6 unknowns because I have 2 degrees of freedom, V1 and theta 1, V2 and theta 2, and V3 theta 3. I also have a uniform distributed load for the element number 1, so I have this column vector that shows up, and this column of concentrated forces that could be applied. For element number 2, same idea. It occupies this space, but the length of the beam of that element is B. That's the only difference now. And there's no distributed force. If you look at the problem statement, element number 2 has no distributed forces there. So in reality, I can now I can assemble these 2 elements into a super element here, global assembly. And I've done that. You can use element code number. That's the preferred way if you're going to use a MATLAB or code that automatically does that. But you can go ahead and do that. And you can see here that these are the unknowns. And I'm ready now to apply the boundary conditions. It's a clamped end. So the slope and deflections are 0. I also have that since these are 0, I do not know the forces at that end. But I know that I have nothing applied in the middle node, only a shear force applied in the very end, and no moment applied in the end. And this distributed force stays here. And now I'm ready to solve for U3, U4, U5, and U6. You can now solve that. Once you know U3, U4, U5, U6, plug it back in here, and then multiply the first row times this column, and that will give you Q1, the reaction force, due to these loads applied. There are beams with axial flexibility. The idea there is that these beams can basically take the idea of the bar and add it to the idea of the beam. So not only these beams can deflect transversely, they can also take axial load like if it was a truss. And so that idea is very simple. All you have to do now is combine efforts, right? So the idea is to combine the bar element with the beam element. The shape functions for bar element are different from the beam element, so you have to be careful. the bar element was using linear shape functions, and this beam element, this particular beam element, is using a cubic order polynomial. So we had to be careful. But the ideas are the same. The ideas are simple in the sense I can combine, I can have a wire element that's able to take axial load, but also can take bending. Why not? You may encounter that. So as a consequence, I can construct an element that has this slope, this axial deflection, this transverse deflection. So I have now 3 unknowns per node. And I can write the equations in such a manner that they represent the full behavior of the structure. So if I now use V as a variable of interest for this beam, and U is the axial deflection, I think everybody can agree that I can approximate the solutions U tilde V tilde equals M bold times this column of unknowns. Now I have 3 unknowns per node, U1, V1, and theta 1. And for the second node, I have U2, V2, and theta 2. But that is beautiful because I'm able to now to turn the problem into a beam that can take axial flexibility. And that's very exciting. So if you work out the math and you use the shape functions that were derived for the bar and the beam, and you work through the problem, you'll find that the stiffness matrix for a beam with axial flexibility looks like this. Is going to look like that. You can see, you can recognize the EA over L and minus EA over L. You can see those showing up with the rest 0 because obviously the beam transverse deflection is not coupling with the axial deflection of that beam. And notice how the nodal unknowns are U1, V1, theta 1 at this node, and the nodal unknowns are U2, V2, and theta 2 at this node. Now I can actually even look at beams that are oriented at an arbitrary angle. So say I have a beam that now is at an arbitrary angle, phi. I can do a transformation and I can look at a local coordinate system like I did for trusses and develop the element formulation for the element in the local system and then bring that to the global system using coordinate transformations. And the transformation for this problem is going to look like that. So I have that transformation here, T bold. Notice I have um, basically three unknowns here, three unknowns at this node, U1, V1, and theta 1. So I have to account for that. And so as a consequence, that's why I have a 6x6 transformation matrix. C is a cosine phi, S is sine phi, phi is the angle of how this beam is oriented. And I can transform now T bold times D bold, where D bold is this. If I multiply D bold by this transformation matrix, I'm able to then find D prime in the local orientation system. And so that these are the formulas you'll be using. And notice that related to theta 1, we have a value of 1 because rotation does not depend upon the orientation of this beam. The rotation is a rotation. That's why there's a 1 associated with theta 1 and theta 2. And then for the forces, it's the same idea. The transformation matrix is the same. Cosine phi and sine phi are the same. F prime equals T bold, F bold, where F bold was basically the global loads applied. And look at how I have F bold prime, which are the local forces acting on this beam. So that's what I have. I have the axial load to the beam, shear load to the beam, and bending moment to the beam in the local system. I have a way of taking it from the global to the local, and that's very exciting. Then finally, I have the distributed forces that are shown here. And these are the Hermitian shape functions. Notice how the transverse loads to this beam do not affect the axial component because the transverse loads only affect the transverse components, not the axial components. And so that's why you see a 0 here and a 0, 0, a 0 here because that corresponds to U1 and U2, the deflections, the axial deflections, while these shape functions really are really for the transverse loading condition. So you can now use these relationships that we derived in previous trust lecture, and kind of re-derived it really quickly here. And the bottom line is that element stiffness metrics in local coordinate system can be related to global coordinate system. So my idea is to derive the local element stiffness matrix and then take that to the global system. Well, then f prime equals k prime times d prime. F prime is t bold f, and f is in the global orientation system now. D prime is in the local orientation system, but I'll convert that to a global by using this quantity here. And now I'm ready to solve for f bold. So I think this to the other side, that's t inverse, but t inverse is the same thing as t bold transpose. I invite you to check that at home. So I get f bold equals this times d bold. And notice how k prime bold is our global stiffness matrix now for the system. So now you can analyze various situations in real life. Very exciting problems you can solve. You can solve a rigid joint, a hinge joint, and now you could have this could act like a bar, for example. This could act like a beam. So that's why this could be useful, is because you could have a combination of situations where beam acts more like a bar or a truss, but it could also act like a transverse. It can actually take transverse loads as well. And so that's the idea of this beam element, is it's more general than the truss element and the beam element by themselves. But combined is even more powerful. And that's the point I want to make with this particular formulation I talked about. If you go to the commercial finite element code, ABAQUS as an example, you can, the Euler-Bernoulli beam is there. It's actually there formulated. Here, beam represents beam. That's the element type, B, for beam element. 3 is the, whether it's a 2D problem or a 3D problem. So you can have a beam that's oriented in a 2D space or oriented in a 3D space. That's what this 3 means. And then here, 1 represents a linear element. In the class, we're deriving 3 there. So there's a 3 here, and that 3 represents a cubic element. That's what that means. Okay. Okay, so the element we derive is B23. They're available in ABAQUS standard. And notice that the assumptions I talked about in this class match what ABAQUS says. These elements do not allow transverse deformation. Plane sections initially normal to the beam cross section remains plane. Beams made of uniform material, typical dimensions in the cross section should be less than 1/15 of typical axial distances. Euler-Bernoulli beam elements use cubic interpolation, which we actually derived, and the theory manual in ABAQUS also shows them that. My point there was to show you that what I taught you is consistent with what codes use today. Yeah, so the beam elements are approximating the behavior. So it's not a perfect solution, but there will be some axial deflection associated with the beam deflection themselves. What this is covering for is additional axial load that comes from applying an axial load. And so if you were to have a beam that's subject to axial load, but also transverse load, the stress in that beam is not just equal to P divided by A from axial load applied P, but it's also the stress due to the bending moment applied, which is MC over I. So the stress is going to be equal to P over A plus NC over I, and that needs to be accounted for in this formulation, and that's what the element I just showed you does. It accounts for both effects. With beam deflecting, you of course will get some amount of axial deflection, but the point is that um, we added another degree of freedom to account for the real axial deflection, the real axial load applied. So let's look at how the ABAQUS finite element implementation works. The way it works is that you define a nodal coordinates for this particular problem. I have a beam here, a beam there, and I apply a load of 9,000 pounds, and the idea is to find what is the deflection. In this case, it matters because it behaves like a truss, but also it behaves like a beam. And so the element formulation in ABAQUS accounts for both, which is kind of cool. And all we've done here is provide the nodal quantities for the coordinates of these nodes. So I have 3 nodes, 1, 2, and 3. And this one is the only one that's free, by the way. I define an element connectivity. So for element number 1, I'm connecting nodes 1 and 2. And for element 2, I'm connecting nodes 1 and 3. So that's done by hand. The beam section that I'm using is rectangular, although ABAQUS has many others that could be used successfully. Okay. And then finally, you can apply the material properties of aluminum here. And then you can fix the nodes 2 and 3. Here we have it clamped. Um, and then you can apply a load in the one direction as shown here. So we're fixing it and then applying a 9,000 pound load. You can see here an example using symmetry. You can see here that because it's a symmetric problem, you can probably use symmetry and model one element. And that's what I was done here. I applied a roller support with half this load. And then I have that. Notice that here on the beam section, I put 1 inch squared. I'll ask you for that information, what area cross section you have. So it's always good to go to the ABAQUS keyword manual and understand what kind of information they're looking for. Now, if you were to use ABAQUS CE, which is a lot of the ABAQUS tutorials that we have are based upon, is going to ask you for this information in a GUI successfully. Once you do that, half the load, symmetry applied, you can then solve the problem, and you can see that the deflections are the same regardless. Bottom line, this concludes today's lecture, and I hope you enjoyed it. It's very important to use beam elements to simplify finite elements that are very large, because you don't want to be modeling stiffeners, longerons with 3D elements. They're computationally expensive, and so we want to save those elements for something else that can be represented with 3D elements, which is not a lot, to be honest. And we showed you that last week. All right, with that said, thank you so much.